Welcome to Summarize Science, where we break down the latest breakthroughs in research for everyone. Today, we are diving into an exciting development in artificial intelligence, making AI-generated videos truly understand and obey the laws of physics. Have you ever noticed how AI-generated videos, while visually impressive, sometimes feature objects moving in ways that feel a bit off, maybe floating unnaturally or deforming strangely? This is because many current video generation models focus on making things look photorealistic, but they often lack a fundamental understanding of physical plausibility and how objects interact in 3D space. That's where a new framework called PhysCtrl comes in, aiming to revolutionize how AI creates videos by grounding them in real-world physics. PhysCtrl, short for Generative Physics for Controllable and Physics-Grounded Video Generation, is designed to overcome these limitations. The core idea is to give AI models not just visual information, but also explicit control over physical parameters and external forces. Instead of just guessing how an object should move, PhysCtrl learns the actual distribution of physical dynamics. Think of it like this. Current AI might draw a ball, but PhysCtrl teaches it what a bouncy ball is versus a squishy ball, and how each would react if you applied force. As seen in Figure 1, the system allows for generating physics-plausible motion trajectories across various materials like plasticine, rigid objects, sand, and elastic substances. It even lets you control specific physics parameters, such as Young's modulus for elastic materials, which dictates how easily something deforms and the amount of force applied. So, how does PhysCtrl actually work? The process starts with an input image, along with user-specified physics parameters and applied forces. First, as depicted in Figure 2, the system lifts the object from the input image into a 3D point cloud. This means it transforms the 2D image into a 3D representation made up of many individual points, which is a flexible way to represent different kinds of materials. Next, a special AI component called a generative physics network takes over. This network is a diffusion-based model, which is a powerful type of AI that learns to generate complex data, in this case, realistic physical movements. Conditioned on the physics parameters and forces you provide, it predicts how these 3D points will move over time, creating a trajectory for each point. These predicted 3D point trajectories are the secret sauce. They serve as strong control signals for a separate, pre-trained video generation model. Essentially, PhysCtrl tells the video model exactly how the object should move, ensuring the final video is not only visually appealing, but also physically correct. To achieve this, PhysCtrl needed to address two key challenges. First, what's the best way to represent physical dynamics for AI to control video? The paper proposes using 3D point trajectories, which are versatile for different materials and seamlessly integrate with video models. Second, how do you teach an AI the intricate rules of physics across different materials? To tackle this, the researchers built a massive synthetic dataset of 550,000 animations. These animations, generated by physics simulators, cover 4 material types: elastic, sand, plasticine, and rigid, capturing complex and realistic dynamics. This extensive dataset is crucial for the AI to learn a broad understanding of physics. Furthermore, as shown in Figure 3, the diffusion model itself incorporates a novel spatiotemporal attention block. This allows the AI to effectively see how neighboring points interact in space and how those interactions evolve over time. It's like giving the AI an intuitive understanding of particle interactions, similar to how physics simulators work. Finally, to ensure maximum realism, physics-based constraints are directly embedded into the training process. This means the AI is constantly checked against fundamental physical laws, preventing it from generating implausible movements. For example, one constraint, called physics loss, helps ensure that the deformation of materials, like an elastic object, follows realistic rules during movement. Another constraint, the boundary loss, prevents objects from unrealistically passing through surfaces, like the ground, as detailed on page 6. The results of PhysCtrl are quite impressive. Figure 4 provides a qualitative comparison with existing video generation methods. You can see how PhysCtrl generates videos where objects move according to the applied force, unlike other models that might fail to reflect physical laws or struggle with complex motions like rotations and depth changes. For instance, the chair in other models might not move as requested, but with PhysCtrl, it accurately responds to the upward force. Quantitative evaluations, like those in Table 1 on page 7, show that PhysCtrl significantly outperforms other state-of-the-art models in terms of semantic adherence, meaning how well the video matches the text prompt and force direction. It also scores highest in physical common sense, indicating its superior ability to generate intuitive and plausible physical dynamics and in overall video quality. Figure 5 illustrates PhysCtrl's precise control over physics parameters. You can observe how the same object, when given the same force, deforms differently based on changes in its Young's modulus, just as it would in the real world. This level of control opens up new possibilities for designers and animators. The method also excels in generating realistic motion sequences, as seen in the qualitative results in Figure 6 on page 8, closely matching reference physical movements. The ablation study, presented in Table 3 on page 9, confirms that the spatial attention, temporal attention, and especially the physics loss are crucial for PhysCtrl's superior performance, making its trajectory generation much closer to the ground truth. It's clear that each component plays a vital role in achieving physically accurate and high-quality results. So, what does this mean for the future? PhysCtrl represents a major step towards making AI-generated content more realistic and controllable. Imagine game developers creating characters and environments that naturally interact with their virtual worlds, or filmmakers generating complex special effects that truly obey physical laws without manual keyframing. Designers could prototype products and see how different materials would behave under various stresses, all within an AI-generated video. It democratizes access to high-fidelity visual tools, making advanced simulations available to a wider audience. However, the researchers also acknowledge limitations. Currently, PhysCtrl mainly focuses on single-object dynamics across 4 material types, and it doesn't yet cover highly complex phenomena like multi-object coupling or intricate boundary conditions. Future work will undoubtedly aim to address these limitations and expand PhysCtrl to more diverse and complex physics phenomena, bringing AI video generation even closer to real-world fidelity. It's also important to consider the societal impacts. While PhysCtrl offers incredible creative potential, high-fidelity generative models could, if misused, create deceptive content like fabricated disaster footage. As mentioned on page 16, the researchers are committed to implementing safeguards, such as controlled access and research-only licenses, to mitigate these risks. This ensures the technology is used responsibly and for positive advancements. In summary, PhysCtrl is a pioneering framework that teaches AI the language of physics, transforming video generation from purely visual mimicry to a deep understanding of how objects move and interact. By generating physics-plausible motion trajectories and offering explicit control over material properties and forces, it paves the way for incredibly realistic and controllable AI-generated videos. This innovation promises to unlock new possibilities across industries, making digital creations behave as authentically as anything in the real world. Don't forget to like this video, subscribe to Summarize Science for more breakthroughs, and let us know what you think about PhysCtrl in the comments below. Thanks for watching.